will start a new series called Down the Complexity Ladder. In each episode, we will deal with a certain topic, and we will see the ways we can approach it going down in complexity. So this first episode will deal with linear recurrence relations. So what is a linear recurrence relation? First, we have to ask ourselves, what is a recurrence relation? So basically, a recurrence relation is whenever we have a sequence, say a of n, and we define a of n as a function of n as well as previous values of a of n, namely an minus 1, an minus 2, all the way up to a0. So I'm pretty sure you know many recurrence relations. For example, the factorials. We can define n factorial as being equal to n times n minus 1 factorial. And if I named my factorials as being a of n equal to n factorial, then I can rewrite this as a of n is equal to n times a of n minus 1. You can see here that I defined a of n in terms of n and a of n minus 1. And this is precisely what I meant when I said that a of n is a function of all these variables. Another very famous recurrence relation is the Fibonacci numbers. We know that a of n is equal to a of n minus 1 plus a of n minus 2 with some initial conditions. Like here, the initial condition will be that 0 factorial is equal to 1, and here we'll have two initial conditions, a of 0 equals f of 1 is equal to 1. So this is also a recurrence relation. F of n is defined in terms of f of n minus 1 and f of n minus 2, but if you can notice, there is a difference between these two recurrence relations. Here, the variables that we mentioned here are put together using multiplication. Basically, I am multiplying this variable times this variable, whereas here the variables are simply put together using only addition. So when this is the case, when the variables here are a linear combination, meaning that f of n is defined in terms of these variables as being a sum of these variables times a constant. So I can have 2n plus 3 a of n minus 4 a of n minus 1 and so on. So basically each term here is a coefficient times one of these variables, and I cannot have something like a of n minus 1 times a of n minus 2. So when this is the case, we say that it is a linear recurrence relation. So the Fibonacci numbers are linear, whereas the factorial isn't. So in this episode, we will see many ways how we can calculate sequences that are linear recurrence relations. And throughout this lecture, I will use the Fibonacci numbers as the default example, but we will extend these ideas to other examples as well. So let's consider our first approach. And this is basically the first thing that comes to mind. So we have a recurrence relation here. Why don't we use recursion to calculate it? And we could write something like this to accomplish that. We can define a function that returns a long, for example. So long of fib, we will give it some int n, and it will have a breaking case. So if n is equal to 0 or n is equal to 1, we will just return 1. Otherwise, we will return fib of n minus 1 plus fib of n minus 2. And to illustrate this, let's see what will be the function calls that will happen if we call fib of 4, for example. So if we call fib of 4, this will not be checked, so it will return fib of 3 plus fib of 2. So it will need to calculate fib of 3, and it will also need to calculate fib of 2. Now we are inside fib of 3, so this check does not happen again, so we need to calculate fib of 2 and fib of 1 this time. And again, now we will be inside fib of 2, so we will need to calculate fib of 1 and fib of 0. So when we reach fib of 1, we will just return 1 here. We will also return 1 here. This will return 2. Fib of 1 will return 1. So fib of 3 will return 3. And fib of 2 will also call the same things again. So it will call fib of 1 and fib of 0. So this will return 1 and this will return 1. So fib of 2 will return 2. And finally fib of 4 will return 5. So as you can see, this is quite a tree, and we make lots of function calls, and you can see how this will get even larger for larger values of n. And something else to notice is that we make repetitive calls here. So we calculated fib of 2 twice, we calculated fib of 1 3 times, and we calculated fib of 0 2 times. So let's actually build this table. So we have fib here, and here we will have the number of calls. So 4 was called once, 3 was also called once. So 4 was called once, 3 was also called once, 2 was called twice, 1 was called 3 times, and 0 is called twice. And if we extend this example to calculate fib of 5, it will have this left subtree, and for its right subtree it will have the following. So basically it will call fib of 4 as well as fib of 3. And if we rebuild this table, we will see that 5 is called once, 4 is called once, 3 is called twice, 2 is called twice in this left subtree and once here, so it's called 3 times. 1 is called 3 times in this left subtree and twice here, so it's called 5 times. And 0 is called twice in this left subtree and once here, so 0 is called 3 times. So if you notice, there is a pattern that emerges here. We have 1, 1, 2, 3. Here we have 1, 1, 2, 3, 5. If you extend these examples further, you will see that the number of calls is exactly equal to fib of 0 here, fib of 1, fib of 2, fib of 3, and fib of 2. And in general, the number of calls will be equal to fib of 0 plus fib of 1 all the way up to fib of n minus 1 plus fib of n minus 2. Here when we calculated fib of 4, we made from fib of 0 up to fib of 3 calls plus fib of 2 extra calls. So each time you want to calculate a Fibonacci number, say n, using this method, you will make this many function calls. So your solution will be of order this much. And we can actually simplify this further. So we know that f of n plus 2 is equal to f of n plus 1 plus f of n. And I can rewrite this formula like this. So f of n is equal to f of n plus 2 minus f of n plus 1. So I can apply this to each term here and I will get the following. So this will become, so f of n minus 1 will be equal to f of n plus 1 minus f of n. And the next term will be fib of n minus 2. So f of n minus 2 will be equal to f of n minus f of n minus 1. And the same will go all the way down to f of 2, for example. So this will be equal to f of 4 minus f of 3, and f of 1 will be equal to f of 3 minus f of 2, and f of 0 will be equal to f of 2 minus f of 1. So if I go ahead and add all these together, I will get this sum, and on the right hand side, if I add all this together, this will cancel with this, so will this all the way down, so f of 3 will cancel with f of 3 and f of 2 with f of 2. So at the end I will have f of n plus 1 minus f of 1. So this is the sum of all these elements. And the sum of everything here will be f of n plus 1 minus f of 1 plus f of n minus 2. So this is the exact number of function calls that are done each time I want to calculate the nth Fibonacci number. So the complexity of this approach here will be equal to f of n plus 1 minus f of 1 plus f of n minus 2. And this is of order f of n. And this is exponential, so it is very bad. And the question now is, can we do better than this? And of course we can. If we go back to the tree we draw here, we saw that we calculated some things over and over again. So we calculated fib of 3 here, and we calculated it again here, and the same goes for fib of 2 3 times. So basically it will be nice to avoid recalculating all of this. And if we manage to do so, this tree will get reduced very much. So basically, once we calculate fib of 3 here, and we need it again here, we will just call it. So basically, instead of going through all this, we will basically know that such a node already exists, and instead of drawing this edge, we can go directly to it, and we will get rid of all this. And the same thing will happen here. Once we will calculate fib of 2, if we assume that this will be done in a DFS manner, this is the first fib of 2 that will be calculated. So once we calculate it here, we will know that such a node exists, and when fib of 4 we will make a second call to fib of 2, it can just call this instead of going through all this. Again, this is the first time we will calculate fib of 1, and once we do that, and every time we want to call it again, we can just go directly to that node. So fib of 3 will directly call this, and this will be the first time we calculate fib of 0. And if you can see here, it is like this is a linear array. So we have f of 5 here, f of 4, f of 3, f of 2, f of 1, and f of 0. So there are no arrows from f of 1 and f of 0, and f of 2 has 2 arrows, 1 to 1 and 1 to 0. So we have something like this. F of 3 has 2 arrows, 1 to 1 and 1 to 2. So we have something like this. The same goes for fib of 4. It has an arrow to fib of 3 and another arrow to fib of 2. So this goes to fib of 3 and this goes to fib of 2. And finally, fib of 5 has also 2 arrows, 1 to 4 and 1 to 3. So it has one arrow that goes to 4 and another one that goes to 3. So So we know that this is equal to 1, and so is this. And if we want to calculate f of 2, we can just look at the two previous values. So this will be equal to 2. The same goes for 3, so it will be equal to 2 plus 1, which is 3. So this will be equal to 5, and finally this will be equal to 8. If we want to add another value, we can just go right here and calculate the two previous values. So this will be equal to 13. And you can see how this is much easier than having to draw another right subtree here and consider all this to be the left subtree. And this will be our second approach. So our second approach is based on the idea of memoization, which is a concept in dynamic programming. So I invite you to research these terms, and basically the idea behind this is the same as the concept DRY, famous in computer science. Don't repeat yourself. So once we calculated something, we should not do it again. We could actually implement it right here. So we could have some array of values. Say for example, we have an array of ints or an array of long that we will call scene, for example, and it will have size n that is up to this. And at the beginning we will initialize all these values with -1, and here we can just add a check. So if scene is different from -1, I mean scene of n is different from -1, then we know that this was already calculated. So we'll just return scene of n. And if that's not the case, we will have to calculate it, but once we calculate it, we will set scene of n to be equal to this. Then we will return it. And basically this is pretty much what we did here, but there is a nicer way of implementing it that we will see. And so this way of implementing things would be top to bottom. So we don't know the answer for n, we ask for n-1 and n-2 and so on. And once we found all the answers here, we back up to get the answer to n. So this is a top to bottom approach. The other way of implementing this that we will see here will be a bottom-up approach. So we start from what we know. We know that fib of 0 is equal to 1 and fib of 1 is equal to 1. So these informations will be enough for us to know what is the value of fib of 2. So fib of 2 will be just the sum of the two previous values. So it will be equal to fib of 0 plus fib of 1, and this will be equal to 2. So in order to implement a bottom-up approach, we need to make sure that at each state, all the things that this state depends on has already been calculated. So once we know this, we can know that we can calculate fib of 2. So then we can calculate fib of 3 as being equal to the two previous values. For example, we cannot jump to calculate fib of 4, then go back to calculate fib of 3. So we have to do that sequentially in such a way that once we reach a state, we are certain that all the values this state depends on have already been calculated. So in code we can either define an array, so we will call it like fib of n, it will have size n, and as we did here we will set fib of 0 to be equal to fib of 1, and this will be equal to 1. Then we will have a for loop for I equals 2 all the way up to I is less than or equal to ni plus plus. Then we will just set fib of I to be equal to fib of I minus 1 plus fib of I minus 2. And at the end we will just return fib of n. And as an aside, we can optimize this even further but only in terms of memory. So here the memory complexity of this is O of n, because we declare this vector or this array of size n. So we allocate this much memory. Instead of using that much memory, we can use simply 3 longs a, b, c. So we say a equal to this, b equal to this. Then each time we go through this loop, we first set c equal to b. Then we will set b to be equal to a plus b. And finally, we will set a to be equal to c. So basically, b got the value for fib of I, and a got the value of fib of I minus 1. And at the end, we will just output b. So what is the complexity in this case? In this approach, we used this for loop, so we went through all the values from I equals 2 all the way up to n. So our complexity is linear. And now again we ask ourselves, can we do better than O of n? And in fact we can. So this third approach requires some background in linear algebra and matrices. So as a refresher, I will talk about matrix multiplication. But before that, let's see what is a matrix. So a matrix is a rectangular array of values, objects, or symbols. And what I mean by rectangular is that it has a certain number of rows and a certain number of columns. So for example, this is a 2 by 2 matrix and it has the following elements. This is a 3 by 2 matrix, so I have 1, 2, 3, 4, 5, and we can multiply two matrices only if this one has size AB and this one has size BC. Basically, the number of columns in this matrix have to be equal to the number of rows in this matrix. For example, we cannot multiply these two matrices because the number of columns here is 2, whereas the number of rows here is 3. But if we added another column here and this became something like this, then in this case we can multiply these two matrices. And if we do so, we will get the following. So when we multiply these two, we end up with a matrix of size AC. Like in this example, we're gonna multiply 2 by 3 by 3 by 2, so we'll get a matrix of size 2 by 2. And this first value depends on this row and on this column. And to get these values, we simply multiply like this. And we add across. So 1 times 1 is 1, 3 times 2 is 6, and 4 times 3 is 12. So we get 19 here. And if we do so with this row, we will get 2 plus 27, so 29. And here we will get 4 plus 15, 19, plus 24 will give us 43. And finally here we will have 8 plus 54, which should give us 62. So I invite you to investigate this further if you're not very familiar with this. And now let's see how this relates to our problem. So let X be a matrix. I want you to find such an X such that it satisfies this equation. Is equal to X times f of n plus 1 f of n. So why is this relevant? So if we know the value of f of n and f of n plus 1 and we know this x, we can just multiply these two to get the next value f of n plus 2. Maybe this will be useful, but we first need to find this matrix X. And in order to find it, let's first talk about its size. So what should be its size for this to be consistent? So the size of this is 2 by 1. We have 2 rows and 1 column, and the size of this is 2 by 1 as well. So basically we have no choice for this. We said that it has to be equal to this, so this is A2. And for this to be equal to this, we need to have A2 here. So basically this is a 2 by 2 matrix. Let's try to construct it. So we will have f of n plus 2 here. Here we will have f of n plus 1 is equal to some 2 by 2 matrix times this. So the result, let's consider this second row first. Here the result will be f of n plus 1. And here this column will be multiplied by this row. So do we have an f of n here? We don't. So we should have a 0 here. What about f of 1? We have an f of 1 here. So we should have a 1 here. And if we multiply this way, we will get f of 1 times 1, which is equal to 1 plus 0 times f of n, which will give us f of 1. So that works. We are good to go with this second row. What about this first row? Here f of n plus 2 should be equal to something times f of n plus 1 plus something times f of n. And we of course know that by definition f of n plus 2 is equal to f of n plus 1 plus f of n. So if we just have 1 and 1 here, we will have f of 1, f of n plus 1 plus f of 1. We will have f of n plus 1 plus f of n, which will give us f of n plus 2. So this is the matrix X we were looking for. So let's go ahead and apply this. So let's say we start with f of 1 and f of 0, so they are equal to 1. And then we multiply them by our matrix 1, 1, 1, 0. So here the value here will be 1 times 1 plus 1 times 1, which is 2. And here we'll have 1 times 1 plus 0, which is 1. So we got ourselves f of 2. And we can repeat this process again, but now starting with f of 2 and f of 1. So we'll have 2, 1 times this matrix again. So here we will have 2 plus 1, which is 3, and here we will have 2. So we got ourselves f of 3 and f of 4 and f of 2. And we can go ahead and repeat this process n times to get f of n, but this will be no better than the previous approach. In fact, it may be even worse. But let's notice something. So from here we see that f of 3, f of 2 was equal to this product. So it was equal to the product of 1, 1, 1, 0 times 2, 1. But what was 2, 1 to start with? It was again this matrix times 1, 1. So basically we just multiplied by this matrix twice. And matrices behave in the same way as do normal numbers when it comes to exponents. So we can write this as just being the matrix 1, 1, 1, 0 squared times 1, 1. And this gave us f of 3. So for example, if we wanted f of 100, we will just calculate f of 100, f of 99 will be equal to this raised to the 99th power times 1, 1. So this is great, but we still don't see how this is any better than the previous approach. However, if you are familiar with binary exponentiation, then a bell may have rung in your head when you solve this. So like in this example, we want to calculate this matrix. I'll just call it x again, raised to the 99th power. So you can see this as being equal to x raised to the 98 times x, and you will repeat this 99. But you can also see this as being equal to x raised to the 49th power times x raised to the 49th power times x. As you know, x raised to the a times x raised to the b is equal to x raised to the a plus b. And again, we don't have to calculate x raised to the 49th. We can just see that it is equal to x raised to the 24th times x raised to the 24th times x. And basically what binary exponentiation does, it keeps on breaking this further, so then we will get x raised to the 12th times x raised to the 12th. Then this again will be x raised to the 6th times x raised to the 6th. Then this again will be x raised to the 3rd times x raised to the 3rd. Then this will be equal to x times x times x. And finally x raised to the 1st will be just equal to x raised to the 0 times x raised to the 0 times x. So we know that anything raised to the 0 is just equal to 1, but more precisely it is equal to the identity. But what is the identity here? The identity for matrices is denoted I of n, and it is just the matrix that has all entries equal to 0 except the diagonal here. So our identity will be I of 2 because we have a 2 by 2 matrix. So all other values will be zeros except the ones on the diagonals. And you can see that if you multiply any matrix by this, you will always get the matrix you started with. So when we reach this bottom position, we will just return this times itself times x. So this will be equal to x. And once we get this value, we can just perform 3 multiplications to get the value for x to the 3rd. Then we will just perform another multiplication here to get x to the 6th. Then another here to get x to the 12th, then another here to get x to the 24th, then 2 other multiplications here to get x to the 49th, then 2 multiplications here to get x to the 99th. So you can see here that the multiplications we made are way fewer than the 99 we had to make here in this approach. And in general here, binary exponentiation only does log of the exponent many multiplication. However, there is a difference here between this multiplication between matrices and the regular multiplication we will do. For example, if we were calculating 3 raised to the 99th power, here we assume that multiplication is done in constant time, but it's not the case here. The normal approach to multiply 2 matrices of size k is done in O of k cubed. So basically we have to loop over k square values, and for each value, like here, to calculate this value, we multiply this row by this column, and basically we loop through this row and we loop through this column at the same time. So we did k multiplications here. So going through k square values and doing k work each time will give us a total complexity of k cubed. So the total complexity of this approach will be log of n times 2 cubed. 2 here being the size of our matrix. And I will not go over the implementation of this method in the video, but I will leave a link to more details in the description box. And now enough with the Fibonacci numbers. Let's see other examples when this approach can be useful. So let's consider this question. What is the number of ways to get some x by throwing dice having faces from 1 to 6. So let's say the sum you got was 3. So how could you have gotten 3? You may have made 3 throws and each time you got 1, or you made 2 throws, once you get 2 1 and another time you get 1 2, or you just made 1 throw and you got 3. So here again we can represent our answer as being equal to f of 3 being the number of ways to get sum equal to 3, and we may have gotten 1 in the first row. So if that was the case, we need to calculate the number of ways to get 2, because once we know the number of ways to get 2, we will just add them all to the number of ways to get 3, because each one of these ways can lead to 3 if we just add 1 to it. Also, we could have gotten 2 as a first row, and this will lead to f of 1, and we may have gotten a 3 for the first row, and this will lead to f of 0. And this again, we may have gotten a 1 in the first row, so this will get to f of 1, and this will get to f of 0 if we got 2 on the first row. And in this example, we cannot consider a row of 4 or 5 or 6 because they will be too large for this sum. But if we had f of 6, then all these will be possible. And in this answer, f of 3 will be equal to f of 2 plus f of 1 plus f of 0. And in general, f of n will be equal to f of n minus 1 plus f of n minus 2 all the way up to f of n minus 6. Of course, only when these values are possible. So this is also a linear recurrence relation. So we can apply all 3 approaches that we saw to solve this problem. The first one will be just to define a recursive function that returns this if it does not meet the initial conditions that will be here, like the condition that this is less than 0 and f of 0 will be just equal to 1. The second approach will be dynamic programming. Each time we want to calculate f of n, it will be just the sum of the 6 previous values. And the last approach I am interested in is the one we just saw, which is matrix exponentiation. So our goal here will be to calculate f of 6, knowing all the values from f of 0 all the way up to f of 5. And here we will only have values up to f of 1. So we'll have f of 6, f of 5, f of 4, f of 3, f of 2, and f of 1. Basically, if we find this 6 by 6 matrix, then we can apply the same logic we used for Fibonacci numbers. So here, the result of the multiplication of this row and this column should give us f of 6. So basically, we know that f of 6 is equal to f of 5 plus f of 4 plus f of 3 all the way up to f of 0. So we will have all ones here. And so once we multiply, we'll get f of 5 plus f of 4 all the way down, which will give us f of 6. For f of 5, only this should be valid. So we can have a 1 here and all zeros here. And once we multiply, we will get f of 5 plus 0 times f of 4 plus 0 times this for all values, so we'll just get f of 5. And you get the idea. For f of 4, we only need to set this equal to 1 and all other values should be equal to 0, and so on. So f of 2 will have something like this. So this will be 0, this will be 1, this will be 0, and this will be 0. And finally, f of 1 will be like this. And it is important to mention that in order for this to work, we need to calculate these values manually, or we can use one of the other approaches to calculate all the values up to 5. So a word about constraints. If I tell you that the sum x is less than 15, then you are fine using the first approach. You can just define that recursive function and you will be fine. But if x is less than 1,000,000, this will clearly not work. However, the linear complexity of the dynamic approach will be fine for this. But if I tell you that x is less than 10 to the 18th, then the dynamic programming approach will TLE. And in this case, you can only use matrix exponentiation. So before we finish this lecture, I will just add one other example that is more advanced and which truly shows the power of the matrix exponentiation approach. So consider we have f of n being equal to 2 times f of n minus 1 minus 3 times f of n plus 7 to the n. So is this a linear recurrence relation? This part is clearly a linear recurrence relation. We only have variables here times coefficients, but we're not sure about this part. But here we can define g of n to be equal to 7 to the n. Then g of n will be just equal to 7 times g of n minus 1. So it is also linear, and the sum of two linear recurrence relations is also a linear recurrence relation. So we want to create our matrix here, and we don't even know what should be in these vectors or in these 3 by 1 matrices here. All we know is that we want to know an f of n plus 1, that's for sure. And if we want to know an f of n plus 1, we better have an f of n here and an f of n minus 1, because that's the only way we know how to form f of n. But in this case, we also need to have a 7 to the n, because without it, we cannot form this f of n plus 1. But we also need to stay consistent. So if the leading coefficient here is n, and we had here f of n minus 1 and here 7 to the n, then here we should have f of n and 7 raised to the n plus 1. So let's see if we can find a matrix that will help us solve this equation. So in order to get f of n plus 1 here, we need to have 2f of n, so we need a 2 here, a minus 3 times f of n minus 1, and a 7 to the n plus 1, or a 7 to the n plus 1. So we may start with 7 to the n plus 1 there and have 7 have 7 raised to the n plus 2 here. So here we will just have 1 for a total of 2fn minus 3fn minus 1 plus 7 to the n plus 1. And fn, we have an fn here, so this will be just equal to 1, 0, 0. And to get a 7 raised to the n plus 2 from 7 raised to the n plus 1, we can have 0 here, and a 7 here. So once we multiply these two, we'll get 7 times 7 raised to the n plus 1, which will give us 7 raised to the n plus 2. So here, for example, if I gave the initial conditions that f of n is equal to 1 and f of 0 is equal to 0, for example, I'll just know to start here with 1, 0, 7 raised to the square, and then I'll just keep multiplying by this matrix to get all the values I want. So that's pretty much it for this video. Thank you for watching. See you some other time. Bye bye.